Hi, I'm Mark Barsamian. In this video, we'll be discussing injective functions, surjective functions, bijective functions, and inverse functions. This material is from section 7.2 of the book, which is titled one-to-one functions, onto functions, and inverse functions. We'll see that the terms one-to-one and onto are synonymous with these terms that I used earlier, injective and surjective. So first, we'll talk about injective functions. So the words f is injective, or f is an injection, or f is one-to-one are used in the following situation. We have a function f that has a domain that's some set x and a codomain that's some set y. And what these words mean is this. If two inputs cause outputs that are equal, then the inputs must be equal. So written formally, that would be this. For all inputs x1 and x2 in the set capital X, if the outputs f of x1 and f of x2 are the same, then x1 and x2 must have been the same input. Now there's a contrapositive of this statement that says this. If the two inputs are not equal, then the two outputs will not be equal. So for all inputs x1 and x2 in the set capital X, if the two inputs are not equal, then the two outputs will not be equal. Now there's another wording for the term injective that will be useful later, and it's the following. For every element in the codomain, that is for every element in this set capital Y, there exists at most one element of the domain that can be used as input to cause that element of the codomain to be output. So that's written this way. For every little y in the set capital Y, there exists at most one x in the set capital X, such that f of x equals y. Notice this does not say that there are any, it just says there cannot be more than one. Now I want to point out a very common incorrect interpretation of the term one-to-one. When students are asked what one-to-one means, the answer they always give is this. For each x, there's one y. It's important to realize that this sentence is not what it means to be one-to-one. In fact, that sentence is what it means for f to be a function. Every function has the property that for each x, there is exactly one y. It has nothing to do with the property of being one-to-one. Because that term one-to-one is so often misunderstood, many mathematicians prefer to use the term injective instead. In these videos, I will mostly use the term injective. Now we should be sure that we understand what it means to not be injective. For that, it'll be necessary to understand the negation of the formal statement that f is injective. So to say that f is injective means this. That's the statement that f is injective. The statement that f is not injective is the negation of that. So realize that the negation of that universal conditional statement is this existential and statement. There exists x1 and x2 in the set capital X such that f of x1 equals f of x2, that is the outputs are the same, and x1 is not equal to x2. So there exist x1 and x2 in the set capital X such that x1 and x2 are not equal, but they cause the same output. Let's go on. Example 1. Which of these functions are injective and which ones are not injective? Well, notice this function has two inputs that cause the same output. Let's look at the next function here. Notice that there are no two inputs that cause the same output, so this one is injective. Look at this third one. Inputs A and B both cause an output of P. Inputs D and E both cause an output of Q. So this is not injective. This example is injective. This example is not injective. This example is not injective. Let's go on. Let's consider graphs of functions and of injective and non-injective functions. A function whose domain and codomain are subsets of the real numbers can be illustrated using a graph, but there are graphs that don't correspond to functions. The vertical line test articulates which graphs qualify to be graphs of functions. So the vertical line test for a graph to be the graph of a function is this. If for every little a in set capital A, if the vertical line x equals a intersects the graph exactly once, then the graph is the graph of a function with domain capital A. That is, you say that the graph passes the vertical line test. On the other hand, if there exists a little a in the set capital A such that the vertical line x equals a does not intersect the graph or intersects the graph more than once, then the graph is not the graph of a function, and we say that the graph fails the vertical line test. Now, the injective or non-injective property of functions has a corresponding behavior of the graph of the function as well. The correspondence is what's often called the horizontal line test. The name actually needs to be more precise. I'm going to call this the horizontal line test for injectivity. Looks like I messed up on my type setting here. So suppose that you have a set capital A that's a subset of real numbers and a set capital B that's a subset of real numbers. And function f is a function with domain capital A and codomain capital B. So capital A are the inputs and capital B are the outputs. Well, if function f is injective, then for every b in set capital B, the horizontal line y equals b intersects the graph of f at most once. That is, we say that f passes the horizontal line test. If f of x is not injective, that is, if it's not one-to-one, then there exists a number little b in the set capital B such that that horizontal line y equals b intersects the graph more than once. So f of x fails the horizontal line test. So I want to talk now about functions given by a formula. This example, let f of x be this function, f of x equals x squared. Is function f of x injective? And this should say is f one-to-one. Prove or give a counterexample and illustrate using a graph. Well, this function is not one-to-one, so not injective. Notice that if I let x1 be the number -3 and let x2 be the number 3, then notice that I have two numbers that are not the same, two inputs that are not the same, but they cause the same number to be output. Now, the instructions say to illustrate using a graph. We see that that horizontal line y equals 9 intersects that graph twice. Now notice there are some lines that don't intersect the graph twice. This horizontal line, y equals 0, only intersects the graph once. And this horizontal line doesn't intersect the graph at all. That's okay. The problem is this line. For a function to be injective, for it to be one-to-one, you cannot have a horizontal line touch the graph more than once. Example 3. Let f of x be this function, f of x equals 4x minus 5. Is f injective? That is f one-to-one? Well, in this case, it is one-to-one. Now, how do we prove that? Well, for that, we have to do a general proof. So how do we prove that something is one-to-one? Remember that we have to prove this. Notice that's a universal conditional statement. So we will prove this using a direct proof. So we have no choice about how this proof will start. We have to start by introducing a generic particular element. Now remember what that is. That is elements of the domain that satisfy the condition given in the hypothesis. So we have no choice about what goes in statement 1. Now we have no choice about how we have to end as well. We have to end with the statement that's the conclusion. So there's our gap that we have to bridge. We have to get from here to here. Well, let's just work forwards from statement 1. To say that f of x1 equals f of x2 means the following. Now we see we've actually bridged the gap. Our red statement can be numbered statement 4. And the justification for that statement is that we divided by 4, and there's our proof. Now we have to illustrate using a graph. Now for that I'm going to move this stuff that I wrote up so it doesn't take up so much space. So let's make a graph of our function. So there's the graph of our function, f of x equals 4x minus 5. Notice that there is no horizontal line that touches that graph more than once. Let's go on. Example 4. Let f of x be this rational function. What is the domain of this function? That is the natural domain. We see that the domain is all x's that are not equal to 3. So I'm going to call that by I'm going to give that set a name. I'm going to call that set A. What's the codomain? Well, remember the codomain just means where is the set where the outputs live? Well, the result of doing this computation will be a real number. So the fastest way to answer this question is just say the codomain is real numbers. Question C is what's the range of f of x? That is, what is the following set? The image of set A, that is the set of y values that you get when you use x's in that set A above. Well, for that question, it helps to think of the formula for f of x as an equation involving x and y, and to solve that equation for x. So we've solved this equation for x, and we get this new equation, x equals 3y minus 2 over y minus 1. Now you see that that equation can never be true when y is the number 1. So if you look back at our original function, you realize, oh, no matter what x value we use, the numerator of this fraction is never going to equal the denominator of the fraction, because the numerator is x minus 2, the denominator is x minus 3. So since the numerator and the denominator will never be equal, that fraction will never be 1. So it makes sense that the y values that I get from this formula will never include y equals 1. So the range is all y not equal to 1. I'm going to give that set a name. So the range of function f of x is this set B, the set of all y's that are not equal to 1. Is f injective? That is f 1 to 1? Well, it turns out that it is. Now, we will do the same kind of proof, but here we are aided by the fact that we have solved this equation for x in terms of y. We're going to be able to use this fact. So we're doing a direct proof. So remember the statement that we're trying to prove. We're trying to prove that for all x1 and x2, if the outputs are the same, then the inputs must have been the same. So there on this first statement, we have an introduction of elements of the domain that satisfy the hypothesis. Now we have to end with this. All right, well, let's work forwards from the first statement. Since f of x1 equals f of x2, and I've got a typo here, and this should say f of x subscript 2 and then parentheses. Since that equation's true, let's introduce letters to represent those terms. So let y1 be f of x1 and y2 be f of x2, so that means that y1 equals y2. Now let's go back a page. We have this formula that will give us the values of x. Well, since the values of y1 and y2 are the same, these expressions will give the same values of x. So our unnumbered final statement is actually statement number 3. So notice the conclusion from this. If you can take a formula for a function and solve it for x in terms of y, get an equation like this, then that's going to automatically mean that that original function was one-to-one, because you'll be able to do the same kind of trick that we did here. The key thing is we had these equations that were x in terms of y. Any function that has an equation like that can be solved for x in terms of y will represent a one-to-one or an injective function. Now, question E says, illustrate our results from A, C, and D using this graph of f of x. So what are our results? Remember, question A said, what is the domain? And we figured out that the domain was all x's that are not 3. Well, let's go down to the graph. Notice that this vertical asymptote occurs at x equals 3. You can see that every vertical line that is not x equals 3 intersects the graph exactly once. So every vertical line of the form x equals a, where little a is a number in the set capital A, intersects our graph exactly once. Now let's go back up and see the answer to question C. Question C was, what is the range? That is, what is the set of y values that actually come out on the graph of the function? Well, we see that every horizontal line of the form y equals b, except this one. This is the horizontal line y equals 1. So every other horizontal line touches the graph. So all of those horizontal lines of the form y equals b, except one that is y equals 1, all the other ones do touch the graph. So all of those y values are y values that can be achieved on this graph. Those are all outputs that correspond to some input. Now what about the question D? Prove that this function is, or illustrate that this function is injective. Well, the key thing is that there are no horizontal lines that touch the graph more than once. So what I just wrote in black is an illustration of D. What I wrote in green is an illustration of C. And what I wrote in red is an illustration of A. Let's go on. Now I want to talk about what are called surjective functions. To say that f is surjective, or that to say that f is a surjection, is also spoken f is onto. You use this when a function f has domain capital X and codomain capital Y. What it means is the following. For every element in the codomain, there exists an element of the domain, at least one, that can be used as input to cause that element of the codomain to be output. And so written formally, that would be this. For all y's in the set capital Y, there exists at least one little x in the set capital X, such that f of little x equals little y. Now, what does it mean to be not surjective? Well, let's write down the formal definition of surjective. If I take the negation of that, I get the following. There exists a little y such that for all little x's, f of little x is not equal to little y. In other words, there exists a number in the codomain that cannot be achieved as an output for any input x. All right, well, so for our first example about surjective functions, let's go back to example 1 and indicate which of those functions are surjective. Look at the first diagram. I have an element in the codomain that is not an output for any of the inputs, so this is not surjective. Look at the second diagram. I have two elements of the codomain that are not outputs for any input. But look at the third diagram. Every one of those elements of the codomain is an output, so this is surjective. Look at this diagram. Every one of those elements in the codomain can be achieved as an output. Now look at this diagram. I have three elements of the codomain that are not outputs. And in this diagram, the final diagram, I have an element of the codomain that's not an output. Let's go on. Now I want to talk about graphs of surjective and non-surjective functions. Earlier we saw that for a function whose domain and codomain are subsets of the real numbers, there's a horizontal line test for injectivity. It's actually possible to articulate a similar test for surjectivity. I'm going to call it the horizontal line test for surjectivity. So suppose that A is a subset of real numbers and B is a subset of real numbers and that f is a function from A to B. Well, the surjectivity of the function f, or non-surjectivity, corresponds to some behavior of the graph. If f is surjective, then for every number b in the set capital B, the horizontal line with equation y equals b does intersect the graph of f at least once. That is, f passes this horizontal line test for surjectivity. It's a different horizontal line test than the one for injectivity. If f is not surjective, then there exists a real number b in the set capital B such that this horizontal line with equation y equals b does not intersect the graph. And we'd say that f fails the test in that case. So let's return to the functions presented in the earlier examples and indicate whether each is surjective. So in example 2, we started with this function f of x equals x squared. Is it surjective? That is it onto? Either prove or give a counterexample. Well, it's not onto. We can let y equals -5. Notice that there is no x value that will cause that y value to come out. Now that's our proof, which is a counterexample. Because realize that the statement of f being surjective is a universal statement. To say that f is surjective means for all y in the set of capital Y, there exists an x that can be used as input to give that y as output. The statement that f is not surjective is this existential statement. There exists a y in the set capital Y such that there is no x that can be used as input to give that y as output. So we prove that something is not surjective by just giving an example of a number that's in the codomain that cannot be achieved as the output for any input. All right, we're supposed to illustrate using a graph. So how do we do that? Well, remember this horizontal line test for surjectivity. If a function is not surjective, then there must be a horizontal line with equation y equals b, where b is some number in the codomain that does not intersect the graph. Well, we've got a line right there that we can use. The horizontal line, y equals -5, does not intersect this graph at all. Let's go on. Let's look at example 3. This function f of x equals 4x minus 5. Is f surjective? That is f onto? Well, it turns out it is surjective. So how do we prove that f is surjective? Well, one thing that we can do is start by considering the function f of x equals 4x minus 5 as an equation involving x and y. So there's our equation involving x and y. Notice that it's solved for y in terms of x. Now let's solve this equation for x in terms of y. So there is our equation solved for x in terms of y. Now the amazing thing is that that gives us something that we can substitute in as input into f of x. I'm going to do this in a proof. I'm going to do a proof that f is surjective, and I'm going to do that on the next page. All right, so we are going to prove that f of x is surjective. So that means we have to prove this big statement here. Now notice that's a universal statement, so we will prove this by the method of generalizing from a generic particular element. So it's not a universal conditional, it's just a universal. So the first statement is we just say, suppose that y is a given real number. So there's our generic particular element. So that's how our proof has to start. How does our proof have to end? Well, it has to end with the statement that's that predicate. So we have to end with that statement. Now, how do we get to that red statement? Well, notice that that red statement is an existential statement. It says that there exists an x that has some property. Well, the only way that you can prove an existential statement is to come up with an actual example. So we have to think of an x that will work. Well, the hint is we've got this expression that's an equation solved for x in terms of y. We're going to introduce that as our x that's going to be the magic x. So there's the x that we're going to introduce. Again, we just have to come up with an example. So we have the liberty of just coming up with an x however we can figure out a way to come up with an x. Now we have to show that that x has this property. We have to substitute that x into the function f and see what happens. So we substituted in that expression for x into the expression f of x. Now we have to follow this up with what is f of that stuff. So look what happens. When we use that magic x, it turns out that f of x for that magic x is our given y. So we have found an x value that has the property that f of x equals y. So this red statement is actually the final statement of our proof. It's numbered 3. So that's how we prove that f of x is surjective. Now there was more to this. Let's go back to the previous page. Let's do the illustration using a graph on this page. So remember how you illustrate that a function is surjective. If a function is surjective, then every horizontal line of the form y equals b, where b is in the codomain, will intersect the graph at least once. So there's our illustration that this function is surjective. It's actually just like the illustration that we used to show that this function was injective as well. Every horizontal line does intersect the graph. That shows that it's surjective, and no horizontal line intersects the graph more than once. The same picture shows that this graph is this function is injective. Okay, let's go on. Example 4, we dealt with this rational function. The question is f surjective? Prove or give a counterexample. Well, the key to that is we already talked about the codomain and the range of the function f of x earlier when we were discussing example 4 the first time. Let's go back and look what we did before. So f of x was that function, and the domain was all x's except x equals 3. The codomain, that is the kind of things that come out, are the set of real numbers. And the range, that is the actual y values that do come out, is all y values except the y value y equals 1. So the range was all y's not equal to 1. And on the graph, that looked like this. Every horizontal line of the form y equals b, where b is in that set capital B, b is the set of real numbers that's not equal to 1. Every horizontal line of that form, where b is not equal to 1, does intersect this graph. But the thing is, so the answer to this question is actually kind of tricky. We have to define the domain of the function. Now, we've seen that the codomain that we described earlier was a set of all real numbers, and the range is the set capital B. And basically, since the range is a proper subset of the codomain, that is, there's some numbers that are in the codomain that are not in the range, that means that there are some numbers in the codomain that cannot be achieved as outputs of the function. And that the number that is the only one is the number y equals 1. So our function is not surjective. Let's go on. We're supposed to illustrate this using this given graph of the function f of x. Well, we see that here's a horizontal line of the form y equals b, where b is in the codomain. So this horizontal line y equals 1 does not intersect the graph at all. Let's go on. Now, a function's properties depend on the choice of domain and codomain. That's very important. So what we just saw was that we used the domain, the set A. The set A is the set of all real numbers x such that x is not 3. And we write in function notation f colon A arrow r, where that's a boldface r. So that means that we can feed in any x that we want as long as it's in this set, and we'll get out a number that's a real number. Now we cannot write this simple, because the formula for f of x does not give a y value when x is 3. So the domain cannot be the set of all real numbers. We would say that this formula does not give a well-defined function on the set of all real numbers. It fails to do what a function's required to do. The function's required to give an output for every input in the domain. So the conclusion is the choice of domain is important when you're describing a function. Not just the formula for the function, but the description of the domain. Now, also remember, we just found that the function f was not surjective, because for this number y equals 1 that's in the codomain, that's a real number, there is no x such that f of x equals 1. So we just saw that we describe this as in terms of the range and the codomain. The range is this set of all real numbers y except y equals 1. The codomain was a set of all real numbers. The range was a proper subset of the codomain, and that's why this function is not onto. But what if we did this? Let's define, we've got that function called b, that set called b, the set of all real numbers called y, such that y is not equal to 1. If we use that as our codomain and we write this symbol, f colon a arrow b, then this function that I've circled is surjective. That is, every horizontal line of the form y equals b, where b is in this set, does intersect the graph. So the choice of codomain is important when describing a function. Now, why would you not always do this? Isn't this the nicest thing, to choose the codomain that makes your function surjective, so that every possible number in the codomain can be achieved as an output? Well, the answer to that is go back to the very beginning when we first discussed this function. Here, when we introduced this function, it was easy to see what the domain was. We could look at that formula for f of x and see we can't allow x to be 3. But the range, that is the set of y values that actually come out, it's not so apparent when you look at that formula. So a lot of times figuring out what the actual range of a function is can be kind of tricky. Whereas figuring out what sorts of numbers come out is often very simple, or what sorts of things come out. You look at this formula for f of x, and you can see, well, I'm not sure exactly what numbers are going to come out, but what's going to come out is some kind of number. So the codomain, the idea of identifying a codomain, is it's often very easy to quickly describe the sort of things that come out of a function. That's the idea of a codomain. You have to work a little harder to figure out the range of the function. What are the actual outputs that do come out? Okay, let's go on. Now return to the function from example 2. F of x equals x squared. We found that function was neither injective nor surjective. But what if we define the set A this way and define the set B this way? Well, then if we do that and we say that f of x equals x squared is meant to be used as a function from this set A to this set B, then the function is both injective and surjective. Here, let's look at its graph. So here's a graph of f of x equals x squared. It's just the right arm of that parabola. And notice that I have not included anything down here, and I've not included anything out here. The whole world that we're interested in looking at is right here. And every horizontal line of the form y equals b, where b is in this set, every horizontal line of that sort touches that graph exactly once. So that function is surjective. And notice, none of those red horizontal lines touch that graph more than once. So that function is injective. So simply redefining the function with a restricted domain and restricted codomain, we can turn it into something that is actually injective and surjective. Now let's go back to the example from example 3, the function from example 3. This function, f of x equals 4x minus 5. What if we change the domain and codomain to the set z of integers? So then we'll use the variable n instead of x. So we have this function from z to z described by this formula. Notice that this function is still injective. Now how do we quickly show that? Well, if f of n1 equals f of n2, then n1 equals n2. So that proves that f is still injective. But f is not surjective. Now to see why, let's do this. Let's consider the integer y equals 2. Now we know what value x would have to be in order to get f of x equals y. We would have to use x equals the number 7/4, but that is not an integer. So there is no integer x or n or whatever you want to call it. There is no integer such that f of n equals y equals 2. So the same formula can describe a function that is not surjective if we change what we're using as our domain and our codomain. Let's go on. Now I want to talk about what are called bijective functions. The words are f is bijective or f is a bijection. Another common expression is f is a one-to-one correspondence, but I really don't like that term. It's very common. Our book uses it. I'll have to use it in these notes to some extent to match what they do in the book, but I really prefer to say f is bijective. What it means is that f is both injective and surjective. That is, f is both one-to-one and onto. Now it'll be important to determine when a function is bijective or not bijective, and for that it'll be necessary to know the negation of the statement that f is bijective. So f is bijective means that f is injective and f is surjective. So to say that f is not bijective just means the negation of that. So to say that f is not bijective means that f is not injective or f is not surjective. Let's go on. Now let's go back to the functions presented in our previous examples and indicate whether each is bijective. So let's go back to example 1. So here's example 1. Notice that we only have a single function that is both injective and surjective. All of the other ones fail one or the other. Now let's go look at example 2. Example 2, we were looking at the function f of x equals x squared. We saw that it was neither injective nor surjective, so it's not a bijection. All right, let's look at example 3. We found that example 3 was injective because it passed the horizontal line test that no horizontal lines touch the graph more than once. And it was surjective because every horizontal line does intersect the graph at least once. So this function is bijective as well. Okay, let's look at example 4. We saw that this function was injective, that is, no horizontal line touches this graph more than once, but there is this horizontal line that does not touch the graph at all. So this function is not bijective. But remember, we talked about restricting the codomain to a smaller codomain. So let's go down and summarize that in our conclusion about the bijectivity. So summarizing what we found before, the function f with domain set A and codomain R is injective but not surjective. so not bijective. But if we use a smaller codomain, if we use the set B as the codomain, then the function f is both injective and surjective, so it would be bijective in that case. Let's go on. Now, what would be a formal presentation of the meaning of bijective? Well, to answer that question, we should review the definitions of surjective and injective. To say that a function is surjective means that for every element in the codomain, there's at least one element of the domain that can be used as input to cause that element of the codomain to be output. To say that a function is injective means that for every element in the codomain, there's at most one element of the domain that can be used as input. There's never more than one input that causes the same output. So if we combine those two, we get this. To say that a function f is bijective means this. For every element in the codomain, there's exactly one element of the domain that can be used as input to cause the element of the codomain to be output. Now, how would that be written formally, that is in symbols? Well, it's actually very interesting. So the formal statement says, for all y in the codomain, there exists a unique, this exclamation point means unique, there's exactly one element of the domain such that f of x equals y. So there is exactly one translates into this exclamation point in the formal expression. In light of this discussion, it's worthwhile to add some lines to our definition of bijective. So to say that f is bijective, or that it's a one-to-one correspondence, means that it's both injective and surjective, that is both one-to-one and onto. And in words, we could say that for every element in the codomain, there's exactly one element of the domain that can be used as input to give that desired element of the codomain as the output. And in formal symbols, it's written that way, with that little exclamation point there. Now I want to talk about inverse maps and their graphs. Given a function f from a domain x to a codomain y, the inverse map is denoted this way, f superscript -1. It's a map from y to x, and it's defined by saying that f inverse y equals x means that f of x equals y. In terms of the graph, this means that the point b comma a is on the graph of f inverse whenever the point a comma b is on the graph of f. Now, to make a graph of f inverse by hand, you start with the graph of f of x and a second blank set of x-axes for the graph of f inverse, and find a key point xy equals ab on the graph of f, and interchange the xy coordinates to get a new ordered pair b comma a, and plot that new ordered pair on the axes for f inverse. Do this for a bunch of key points. When you have enough key points plotted, sketch the graph of f inverse. This is equivalent to just doing this. Start with the graph of y equals f of x and flip the graph across the line y equals x to obtain the graph of f inverse. So here are some examples of functions and their inverse maps. So here I took the graph of y equals x squared, y equals e to the x, and y equals x cubed. Now, when I flip these last two, I get the graph of y equals ln of x and y equals x to the 1/3. But this first graph is not a function. This fails the vertical line test. Now you can see that on the graph of y equals x squared, that vertical line would be this horizontal line. So it's because the graph of y equals x squared fails the horizontal line test for injectivity that the graph of the flipped equation, this is the graph of x equals y squared. It's not a function of y in terms of x because it fails the vertical line test. We see that since y equals x squared is not injective, when I interchange the x and y coordinates, I get a new graph that's not the graph of a function. Well, so the question is, when is an inverse map qualified to be called a function, and what properties will the inverse function have? Well, the idea is the graph of f inverse will pass the vertical line test for a function whenever the graph of f passes both horizontal line tests. That is, whenever f is both surjective and injective. Now, the graph of f inverse will automatically pass the horizontal line tests. Let's go back up and look at that. On these graphs, these graphs pass the horizontal line test. Now, why? Well, all of those green lines correspond to vertical green lines over on these graphs of the original functions. Well, these original graphs are functions, so they pass that vertical line test for functions. So when I flip all those graphs to obtain these graphs, those graphs are going to pass the horizontal line tests. So the graph of f inverse will automatically pass both horizontal line tests. So the criterion is really this. Whenever the graph of f passes both horizontal line tests, then the graph of f inverse will pass the vertical line test. So the tricky criterion is this one. The original function f needs to be both injective and surjective for the inverse map to be qualified to be called a function. Well, that's the gist of a theorem in the book. Theorem 7.2.2, when an inverse map will be a function. And the theorem goes like this. If the original function f is bijective, that is injective and surjective, or 1 to 1 and onto, then the inverse map, defined this way, will have the qualifications to be called a function. And in that case, we call this inverse map the inverse function for the function f. So there's always an inverse map, but it isn't always a function. It's only a function in the case that the original function f is bijective. And then what we just discussed about the properties of the inverse function, the fact that the inverse function will pass the vertical line test and it'll automatically pass the horizontal line test, those things are embodied in this theorem. The inverse function will be both injective and surjective. Now, the book gives a proof of this theorem, 7.2.2, but I find a much simpler proof is what I think is one of the coolest things ever in math. So here's my proof. Well, so now what are we proving? We're proving that if f is bijective, then f inverse is a function and f inverse is bijective. Well, so we start by saying suppose that a function f is bijective. Well, that means we're going to have two quantified statements that we know are true. Because f is a function, we know that for every x, there's exactly one y. That's the quantified statement that f is a function. Because f is bijective, we know that for every y, there's exactly one x, such that y equals f of x. Now here's the cool trick. By the definition of the inverse map, we know that this expression, y equals f of x, means the same thing as this expression, x equals f inverse of y. So if we just simply replace this symbol with this symbol in all those places, we get these new statements down here. But look at these statements very carefully. The first statement says, for every x, there's a unique y such that x equals f inverse of y. This tells us that f inverse is bijective. On the other hand, look at this statement. For all y, there's exactly one x such that x equals f inverse of y. That tells us that f inverse is a function. So the proof that the inverse map is a function and that it's bijective is really wonderfully simple if you have these quantified expressions for the fact that f is a function and the fact that f is a bijection. Let's go on. Now, how do you find a formula for the inverse function? Well, think of the formula for f of x as a machine that takes x as input and spits out y as output. That is, y equals f of x. This gives you an equation involving x and y, an equation that's solved for y in terms of x. So what you can do is you can solve the equation for x in terms of y. You get a new equation. Think of that equation as a machine that takes y as input and spits out x as output. That equation describes f inverse as a function of y. So that resulting expression for f inverse of y could be rewritten using another variable if you want, but I prefer to just leave it as it is. Let's go back to our examples. We found that this function, f of x, is a bijection, so it has an inverse function. So our first question is, does this function have an inverse function? And yes, it does, because this function is bijective. Well, so how do we find the inverse function? Well, we start with the equation y equals 4x minus 5 and solve for x. So what we have now is an equation solved for x in terms of y. This gives us the function f inverse. So the equation for the inverse function is f inverse of y is that formula. Now, if you prefer to have your functions have different variables, you could change the variable afterwards. You could say that f inverse of t equals t plus 5 over 4. You could say f inverse of x equals x plus 5 over 4. I prefer to change variables after I figure out what the function is, but to figure out the function, I don't change the variable in the process. I just keep the original variables where they are. I solve for x in terms of y, and I get this result. Now, what about this function, f from z to z, defined by the same formula? Well, does it have an inverse function? The answer is no, it's not surjective. So it's not bijective. Does not have an inverse. Let's go on. What about this function? F of x equals x minus 2 over x minus 3, using this set A as the domain and this set B as the codomain. Well, we saw earlier that when we use those functions as the domain and codomain, that f was bijective. So does f have an inverse function? Yes, because f is bijective. So to find the inverse function, we start with the equation and we solve for x. We did this earlier, but I'll do it again. So the result is this equation solved for x in terms of y. So the inverse function is, okay, well, so that's the end of that example, and that's the end of the video. Thank you.